Hi, in this lesson we'll be looking at differentiation using the chain rule. We will start off with some basic examples. By the end of this lesson you should be able to answer a question like this, so stay tuned. Okay, so before we jump into exam questions, I just want to go through some basic functions and how to differentiate them using the chain rule. So if we have y equals to e to a power of f of x, right? So here we have the exponential function, and the power of the exponential function is f of x, which is some function in terms of x. So if we were to perform dy by dx, first we have to differentiate the exponential function, which gives us the exponential function back, e to the f of x. Then we multiply by the derivative of the power. If we differentiate the power, obviously f of x will differentiate into f dash of x. This is basically the application of the chain rule. You differentiate the outer layer. The outer layer is our exponential, and then the second layer, the layer after that, is the f of x. So differentiate e gives you the same exponential back. Then you times by the differential of the second layer, which is the f of x, that gives you f dash of x. Now obviously if you have more than one layer, you will then differentiate the third layer and times by what that function is, or what that derivative is. So for example, if y equals to e to the power x squared, then dy by dx would be e to the power x squared times by the derivative of the power here. Can you see here f of x is our x squared, so which differentiates into 2x. Another example could be y equals to e to the power of sine x. Therefore, dy by dx would be e to the power of sine x multiplied by the derivative of sine, which is cos x. Okay, so differentiation, its purpose is to give us the gradient function of a curve, which will be needed to work out the equations of tangents and normals to a curve at specific points on a graph. So here is one of those questions. The curve C has equation y equals to 2x minus 3 all to the power of 5. The point P lies on the curve C, which has a coordinate of half comma minus 32. Find the equation of the tangent to the curve C at the point P and give your answer in the form y equals to mx plus c. Obviously, it's a straight line graph, so you need to have the equation of the straight line. Okay, so to work out the equation of the tangent, we need to start by working out the gradient of the tangent. And as we know, the gradient of the tangent to a curve is the same as the gradient of the curve at that point. So the gradient of the tangent, let's call it m, which is in our equation of a straight line, will be the same as the gradient of the curve at that point. And the gradient of the curve is given by working out dy by dx. At what point are we looking at? We're looking at point P, and the x coordinate at that point is a half. So once you worked out what dy dx is, the expression for dy dx, we will then have to substitute in x equals to a half to work out the numerical value of that gradient. So we have to differentiate y with respect to x. Now here, if you explore the function has two layers. The outer layer is the power, so we differentiate the power first. The power comes down and goes down by 1. And then we differentiate the inner layer. So differentiate the outer layer gives you 5 bracket 2x minus 3 and to the power of 1 less, so that's power 4. Then you multiply by the second layer, which is our 2x minus 3, and that just differentiates into 2. We can simplify that as 10 bracket 2x minus 3 to the power of 4. Now, we want the gradient when x equals a half. So the gradient when x equals to a half, so we're going to substitute x equals to a half. Therefore, the gradient of the tangent would be 10 multiplied by 2 times a half, which is 1 minus 3 to the power 4. Let's work out what this is. So 1 minus 3 is minus 2. Minus 2 to the power of 4 equals 3 times 2 is 4. That gives you positive 16, and 16 times 10. So the gradient of a tangent is 160. Therefore, we could say that y is equal to 160 x plus c. And to work out the c in our straight line graph, we substitute the coordinate that it goes through, which is minus a half, a half minus 32. So y equals to minus 32 equals to a half of 160, which is 80 plus c, and that gives you c is equal to minus 32 minus 80, so that's a minus 112. Therefore, y equals to 160x minus 112. And we have the equation of the straight line that passes through the coordinate P, which lies on curve C. Right. Here's another exam question on the application of the chain rule. So we are asked to find the gradient of the curve with the equation y equals to 2 to the power of x squared at the coordinate 2, 16. Now, just a quick recap, if y equals to a to the power x, then dy by dx is equal to a to the power x multiplied by ln a. So that's how we differentiate an exponential function where the base is anything else apart from e. So here the base is a. We can see that we have ln a, which is going to be our constant, and the exponential stays the same as what we have originally here. So if y equals to 2 to the power of x squared, there's two layers to this function. There's the exponential layer, which is the outer layer, and the second layer is the x squared. So when we perform dy by dx, we differentiate the exponential layer first, which is the 2 to the power. So that will give us the same 2 to the power of x squared, multiplied by the ln of the base number 2, multiplied by the differentiation of the second layer, which is the x squared, and that differentiates into 2x. Okay, and now just to simplify this a little bit, so we have this, the constants 2 times ln 2 is our constant, times by x, and then times by the exponential 2 to the power of x squared. You can see here that the base number has to be kept separate from the other two here, because that base here has a power of x squared, whereas this 2 is just by itself. All right, so we want to work out the gradient at this coordinate. So we have x equals to 2 in that coordinate. So substitute this into dy dx. Gives you 2 times ln 2, which is our constant here, times by 2 again. So x is equal to 2 times by 2 to the power of x squared. X is 2, so 2 squared will give us a 4 there. And now we have 2 to the power 4, 2 times 2 is 4, that gives you 16, 16 times 2 is 32, and 32 times 2 is 64 ln 2. Okay, this is one of the harder end of the application of chain rule. Given that x equals to the sec squared of 3y, find dx dy in terms of y, and then we need to show that dy dx is equal to this fraction in terms of x. If you look here, the x is the subject to this formula here, and y obviously is inside the sec. Let's start by differentiating x with respect to y. I would say this expression is actually made of 3 layers here. We have the sec of 3y, and then all of that is being squared. So sec squared, I'm just going to put the bracket around the whole of sec and make it squared. 3 layers, the power 2 is the outer layer, the second layer is the sec, and the third layer is the 3y. Each layer we differentiate and then we times by each of the layer. And in the order we follow is the outer layer first, the second layer, and then the third layer. And that's basically the chain rule in action. So if we now perform dx by dy, first we differentiate the outer layer, that's the power 2 comes down, and we get sec of 3y to the power 1 times by, then we differentiate the sec, and if you look up the formula booklet for the differentiation of sec, that gives you sec times tan. In other words, sec differentiates into a sec tan. And the third layer is to differentiate the 3y, and that gives you 3. And remember, we're differentiating with respect to y this time. So if you differentiate 3y with respect to y, we just get the constant 3. And if we were to tidy this up, we have 2 times 3 at the end. That gives us 6. A sec times a sec, that brings up the power of sec to a 2 again. So sec squared of 3y multiplied by tan 3y. And that's the answer to dy dx in terms of y. Okay, then moving on to part B to the question. Show that dy dx is equal to that fraction. A lot of people, when I've looked through their working out, they tend to jump steps when it comes to show a question, and by doing that, you're actually losing marks. You want to work out dy dx. Now, if you have dx dy, all you have to do is flip the fraction or do the reciprocal on both sides, and that will turn into dy by dx. So here we have dy dx as 1 over 6 multiplied by sec squared of 3y multiplied by tan of 3y. And if we look at what we have here, that's the sec squared of 3y, but we already know that sec squared of 3y is equal to x. So we know that this expression here will turn into x. So just write the x here. And if you look at the final answer here, we have a 6x, and we have here is also a 6x. The problem is this tan. We need to change that tan into something to do with x. So what links a tan and a sec squared together? The identity 1 plus tan squared a equals to the sec squared of a. But we want tan to be the subject, so tan squared a would be equal to the sec squared of a minus 1. Therefore, tan itself would be the square root of sec squared a minus 1. And if we use this here, we have dy dx as 1 over 6x multiplied by tan, which is the square root of sec squared. But in this case, the a obviously is our 3y, so it'll be sec squared of 3y, and then we have a minus 1. And again, if you go back up, sec squared is equal to x. So this sec squared here will change into x. And voila, we have our solution. Dy dx is 1 over 6x times the root of x minus 1. And just to show that, just to match the final answer, we can write the square root as bracket to the power of half, and we have our final answer. Hope you have enjoyed the lesson and feel more confident in applying the chain rule for differentiation in various types of exam questions. Next lesson we'll be looking at differentiation using the product rule and the quotient rule. So I'll see you in the next video.